I could write my CI wave function, which we had last week. I could write them up with those operators as well. And I want to do that so we can compare them to the coupled cluster wave function. So a CI wave function in this notation would then look like CI. That would look like this. Again, I have my Hartree-Fock, and I just let the T act on the Hartree-Fock, just normal. So, because remember, CI was Hartree-Fock plus all excited determinants with some coefficients, and that's what I do here, and Hartree-Fock plus all the other one, because that T generates all single excited with some coefficients, or double excited with some coefficients, and so forth. So that is the CI wave function from last week, just written in that notation. Because now we can compare it with the coupled cluster wave function. But for that we have to know what is the exponential of an operator. Now, the exponential of any sort of kind of function of an operator, be it the exponential, be it the square, be it the square root of an operator, and it's actually the same if you look at what is the exponential of a matrix, the square root of a matrix and all that. You define that by the series expansion of that mathematical function. So we have to know, the only thing we have to know, what is the series expansion of ex, e to the power x. And then we apply that here, which means to know what this does, in practice, we have to expand it in that series expansion. And that means the coupled cluster wave function then is meaning e to the t, Hartree-Fock, that is big parenthesis. Now the expansion is 1 plus x squared and so forth. So I get 1, then I get t, let's write it this way first. Then I get 1/2 t squared, 1/6 t to the third, and so forth. Because it's 1 plus, well, 1 over n faculty, and then so on. Oh, Hartree-Fock. Now we have to insert, or we can insert this expansion in excitation operators, both here and there. I mean, if you do that for the CI first, that just gives us 1 plus T1 plus T2 plus T3 and so forth times, well, again up to T number of electrons times the Hartree-Fock. Whereas here we now get one is, that's easy. Then we get here, if we insert it here, we get T1. And what I want to do now is sort of collect them in the same excitation level. So I get T1, then I get, from this I get T2. That's a double excitation, or that generates double excitations. But if I sort of look ahead, the next term is 1/2 t squared. There's going to be a T1 in there. So I get also 1/2 T1 squared. And that is also generating double excitation, because it makes a single excitation, the first T1, and then comes the second T1 afterwards acting on it. I mean, the square of an operator is just one operator act first, and then the same operator acts on the product of the first one. So that's double excitation then. Then let's look at triple excitations. For triple excitations, of course, I get one from here, T3. Then I can, in the same way as before, I can get, well, from here I can get something. Because here I can get I can get T1 and T2 together. So I can get a T2, T1 term, which in principle should be 1/2 T2, T1. But of course I get that term twice. So I get T2, T1. And then from the T to the third, I get 1/6 T1 to the third. I want to continue that one more to the quadruple excitations. So here I get, from this one I just have T4. Then I guess I can get T3 with T1. That's also quadruple excitation. That comes again from this one. And there are two, depending on whether I have the T1 in the second or in the first of the two of the square. Then from this one I can get, well, I get another one here. I get 1/2 T2 squared. I can get 1/2 T2 T1 squared. And I get 1/24 T1 to the fourth power. And now I stop. So essentially, these two wave functions, not essentially, these two, if I do that up to all excitations, those two wave functions are identical. Identical in the way that they include all the same determinants. They have all single excitation, they have double, triple, quadruple, and so forth excitations. The difference between them is that up here, every excited determinant has one coefficient, which in the CI wave function I determine variationally. Whereas in this wave function, I have more than one coefficient. I have combinations of coefficients for each excited determinant, for all the ones which are higher excited than single excitations. And those coefficients, as I will tell you later, are determined in a different way than the ones up here. But it includes the same excited determinants. Now, there's a bit of, so in a way it's just a repartitioning of the full CI wave function, what I do here. And again, and it is, I mean, if you do couple cluster to the same excitation to the level of all electrons, you get exactly the same result. So if you do a couple cluster calculation on a 2-electron system where you have then, of course, only single and double excitations included there, you get the full CI result. You just get there in a different way, but the result is the same.